Hello and welcome everybody. In today's lecture, I wanted to sort of talk about this introduction to linear regression. And it's sort of a comprehensive introduction to the math and the implementation of this very fundamental algorithm. And we'll also touch on the multivariate and multivariable regression, optimization, gradient descent, and sort of the overall machine learning pipeline that's associated with it. I know that most videos will try to avoid the theory bloat that we make, and we'll aim for the sweet spot of about 10 to 20 minutes, but there are exceptions like this one. But the good news is you can always watch it on double speed, so hopefully that gets you through quicker. But linear regression is a foundational machine learning algorithm, and it's likely that most of you have encountered it before as part of an introductory AI or statistics course you've taken. But today we'll take a deeper dive into its mathematical formulation, its assumptions, and the optimization methods, which are critical for understanding not just linear regression, but also the more advanced algorithms we'll touch upon later on. Linear regression, in fact, is kind of deceptively simple. It's a starting point for many machine learning techniques, and its core ideas, things like the gradient descent and loss minimization, are widely used in much more complex models as well. So let's go ahead and get started. And as we get started, let's go over sort of the objectives that we might have for the talk today. We'll hope to build an intuitive understanding of what linear regression is and why it works. We'll also dive into the mathematical formulation, though, and we'll cover both the scalar equations and the more compact vectorized versions of that. We'll also discuss the key assumptions that linear regression makes about the data. These assumptions are critical for understanding when it'll work well and when it won't work. And also, we'll touch briefly on its limitations and prepare for the next lecture on regularization techniques, things like ridge and lasso regression. All right, so let's jump right in. All right. So here's linear regression, and as I said, it's one of the simplest and most widely used algorithms in supervised learning. We sort of delved into the different kinds of learning that we deal with in machine learning in the last couple of times. So this time, let's dig into this very essential supervised learning algorithm. It's used to predict some kind of a continuous outcome by modeling the relationship between the input features and the target variable as a straight line, or if you're in higher dimensions, as a hyperplane, of course. And the line of best fit minimizes the error between the predictions, as you can see on here, and the actual data points, right? So an example might be you're trying to predict house prices based on square footage. Maybe that's the example that we have over here. Linear regression will find the line that best explains the relationship between the two variables. And let's sort of break it down. The goal is to find the line that best fits the data, and so that it minimizes the error between the predicted values and the actual values. And we can think of the line as some mathematical function that takes an input x and produces an output y. That's our hypothesis function, right? And so in this example, the dots will represent our data points. For instance, the house sizes and their actual prices, things like that. And the line is our model's prediction. The closer the points are to the line, the better the model fits the data. So let's take a look at where this sort of comes from and give it a historical context as well. And it began in the early 19th century with Francis Galton and later Carl Pearson, who took it to the next level. And over the years, it's grown into a fundamental tool in statistical analysis and machine learning. And, originally it started with these simple linear models to explain relationships between variables, but then it quickly expanded into multiple linear regression, and that allowed for examining more complex relationships. Today, it's integrated into machine learning algorithms and plays a crucial role in predictive analytics and data science as well. All right, let's take a look at this. So here's the dependent variable the first thing that we'll be looking at. And that's what we're trying to predict. And the independent variable or the variables, depending on the dimensionality, are the predictors that will help us model the relationship. And this concept assumes, of course, a straight line linear relationship between the dependent and independent variables. That's why we can represent it with a linear equation. And so let's jump right into the mathematical formulation of that linear equation. We'll break that down because first we're seeking some sort of a linear relationship between our features x in the matrix model, right? We'll also look at a couple of different formulations of this, and you'll use the one that's most pertinent and sort of relevant to the problem that you're handling. But in this case, let's assume that we have our features x and our target y. X is, of course, a matrix, and y is our target vector that we have. Each row in X represents an observation, and each column represents some feature. The beta vector contains our parameters. That's what we need to actually estimate. And the error term epsilon captures the noise in our observations. And we usually assume that it follows some sort of normal distribution. That's in the first approximation. We use the squared L2 norm as our loss function. And for our more advanced students, it might be worth noting that this choice isn't arbitrary. It gives us some nice mathematical properties, and it connects to the maximum likelihood estimation under Gaussian noise assumptions that you might normally see. And the quadratic nature of this loss function, which you can see over here. Oops, sorry. Gotta go back. Okay, so I think we're back. And so, as we were saying, the quadratic nature of this loss function ensures that we have a global minimum when x has full column rank. We'll talk about that in just a minute as well. But I do want to touch upon this L2 norm, the so-called Euclidean norm that we have. The L2 norm of some vector v usually measures its length in Euclidean space. And so for some vector we might have it made up of v1, v2, etc., all the way up to vn components. And it's calculated as the square root of v1 squared plus v2 squared plus blah, 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 all the way up to vn squared. And so in this equation, we're computing y minus x beta, and the underscore there, the subscript, represents the L2 norm of the difference between y and x times beta. So when we square that L2 norm, that's that superscript that we have over there, we get basically the components squared and added. This eliminates the square root and gives us kind of a smoother function to optimize. So the subscript over here indicates L2 norm, and the superscript indicates that we're squaring it. And this loss function measures how wrong our predictions are. The loss function of beta measures the total error between our predictions, which are x times beta, and the actual values, which are the y. And the smaller the values for that loss, the better the predictions we have. And this is the least squares objective. The least squares here refers to minimizing the sum of the squared differences, because we're finding the beta that minimizes the squared errors. The right side, y minus x beta transpose times y minus x beta, expands to exactly the sum of squared differences. So we mentioned this idea of a full column rank, and maybe we should talk about that a little bit before we point out why it's so integral to this formulation. Some of you might already have an inkling about both why it's integral and what it is, but a matrix is considered to have full column rank if all its columns are linearly independent. So for the X matrix, this means that no feature can be expressed as a combination of other features. So full column rank ensures that the solution is unique. There's only one beta that minimizes the loss, and that X transpose X is invertible. That's crucial for finding the solution. Maybe a good example for the intuition, because one of our goals is to build up the intuition along the way, might help. If X has columns like height, weight, and then two times height, it would not have full column rank because the third column is just two times the first column. It's linearly dependent. But if X had columns height, weight, and age, then it would have full column rank because none of these can be expressed as a combination of the others. Also, you might be wondering, well, why use the squared L2 norm? Well, that's because it's differentiable. It makes the optimization easier. It penalizes larger errors more heavily, and it leads to a closed form solution. Oh, and also under Gaussian noise assumptions, as we mentioned, gives us the MLE, the maximum likelihood estimate. This objective has deep connections to statistics as well. It's, as we said, it's the same as MLE under Gaussian noise, which is why it appears so often in statistical learning. Oh, and maybe a little term about the terminology of why it's called the least squares objective. You might see that bandied about as well. The term objective, of course, comes from optimization theory, where we want to find the best solution by minimizing or maximizing some function. It's called an objective because it defines our goal, or objective in mathematical terms. In the context of least squares, our objective function is our loss function. They're equal to the same thing in this case. Both refer to the loss of beta, which is equal to y minus xb, the L2 norm squared. Both measure how well our model fits the data, and both are what we're trying to minimize. But the distinction's a little subtle one in general. The objective function, the broader term that's used in optimization, could be something we want to maximize, like profit, or minimize, like error. But the loss function specifically measures the error deviation and is always something we want to minimize. So whenever you might hear least squares objective, it's referring to that mathematical function we want to optimize, some objective function. For us, that happens to measure loss, and it's the loss function, and that's using the sum of squared differences, the least squares. And I guess another intuitive analogy that you might want to think about is, say, you're hiking to the lowest point in a valley. The elevation will be your objective function or your loss function in our case, and finding the lowest point is your objective. So minimizing elevation is reducing your loss. They're describing the same goal from different perspectives, is one way to think about it. But in machine learning, we'll often use these terms interchangeably because we're usually minimizing some form of error, so our objective function isn't always a loss function. In general, sort of terminology is sort of, abused occasionally, especially if you're coming from a pure math background. Just ask any physicist and the direct delta function for more on that. Um, all right, let's see if we can sort of get to more details about this and start to look at the optimization. So the initial least squares optimization of the loss function or the objective function. Let's look at deriving that step by step, right? We've got these three steps over here. We start off by taking the gradient of our loss function with respect to beta. That's the L of beta, and we set it equal to 0. This gives us the normal equations. For our beginning students, if this is the first time you're sort of seeing this, you can maybe focus on understanding why this solution minimizes the squared errors. And for more advanced students, if you've seen this stuff a bunch of times before, you might want to consider what happens when X transpose X isn't invertible. And that's what'll lead us to our discussion of regularization and the pseudo-inverse. But in this section, we're doing the actual least squares minimization. So let's break it down. Let's break down each step and go through it in detail. So in step one, what we're doing is we take the gradient of the loss function with respect to beta, and setting it to 0 finds where the function slope is 0, the minimum point, and that comes from differentiating what we saw earlier. Let me go back. We saw earlier, here we go, the y minus x beta transpose times y minus x beta, and the -2 and the +2 come from the chain rule when differentiating because it's a product. You can work that out maybe as an exercise. And then in that next line that we have, the x transpose times x beta is equal to x transpose y. It's basically just rearranging this previous equation. And it's known as the normal equations in statistics, and it basically just moves all the beta terms to the left side. I hope when I point this way, you're seeing the left side, depending on if the image is mirrored or not. But this is a system of linear equations, and in that third equation, the beta equals x transpose x inverse times x transpose y. We're basically solving for beta by multiplying both sides by x transpose x inverse. This is the closed form solution, and sometimes it's called the ordinary least squares estimator as well, and some of you have probably seen that already. This derivation shows us why we need that full column rank that we talked about. If x doesn't have full column rank, then x transpose x isn't invertible, and we can't compute the inverse, so the solution doesn't exist. And it's called a closed form solution because we get beta directly by computing this formula. There's no need for iterative optimization like gradient descent, which we'll also see in just a bit. But this is one of the few machine learning models with such a nice analytical solution. And that's one of the reasons why we look at it so in so much detail and spend so much time with it. And of course, because it gives us a chance to elaborate the whole machine learning pipeline as well. So, what are some applications of this stuff? Lots of real world applications, right? Some examples could include things like predicting house prices. If you have data on house features like square footage, number of bedrooms, location, etc., linear regression can help you maybe predict the price of a house based on these features. Advertising analytics, marketers use it to predict revenue based on advertising spend. Energy usage model by utility companies. You'd be surprised how much they use just simple linear regression to understand how temperature affects electricity consumption. Even though this linear regression is simple, it's still widely used because it provides nicely interpretable results, and also importantly, it serves as a baseline for more complex models. Despite its simplicity, linear regression is incredibly powerful, and really we use it as a baseline more often than you might think. All right, here we go. Okay, it wasn't clicking for a second there. Let's look at a little bit of a different formulation over here. Instead of the previous matrix formulation, which is usually preferred for advanced applications, we can also do a hypothesis function formulation. And we're going to look at hypothesis formulations later on as well. Do a hypothesis. So this hypothesis function formulation, as opposed to the matrix formulation, can be very helpful as well. And it's another way to formalize linear regression mathematically. At its core, the model is represented as a hypothesis function, which you see over here. The h theta x in this case is the predicted value or output given the input. Oops, where did my cursor go? Given the input x. Theta naught in this case is the intercept or bias term that we have, and oh my gosh, this thing keeps disappearing. Theta 1, theta 2, theta n, etc., are the weights or parameters that determine the contribution of each feature, x1, x2, all the way up to xn, to the prediction. x1, x2, xn are the feature values, the inputs that we have, of course. The cost function is also called the mean squared error, as you can see over here, and it measures how well the model fits the data that we have. In this case, the 2 and the m are these parameters that we're using to calculate the average squared error. It basically simplifies the calculation a bit for us. The division by m, in this case, ensures that we're calculating the average squared error across all data points, which normalizes the cost function regardless of the data set size. And that factor of 2 that we have is added purely for mathematical convenience. It cancels out the 2 that appears when we compute the derivative and simplifies the gradient descent calculation significantly. The h theta xi in this case is the predicted value for the ith data point, and where's this cursor again? There it is. And the yi is the true target value for that ith data point that we have. So the cost function quantifies the error between the predictions and the true values. And our goal, just like previously in the other formulation, is to minimize this cost function by finding the optimal parameters, the theta in this case. The two formulations that we have, the hypothesis function and the matrix form that we have, are basically two equivalent formulations of linear regression. They're just written differently. You could think of it like the matrix mechanics and the Schrodinger formulation of quantum mechanics as well, right? They'll give us the same thing in the end, but one might be easier, more beneficial in one context than another. The hypothesis function h theta x, in this case, is equivalent to the matrix form that we had of x times beta. They're the same because your theta parameters are equivalent to the beta. The X matrix includes a column of ones for that theta naught, the bias term. And writing it in matrix form is just a compact way to write the sum. And we're going to see a vectorized form of this in just a bit as well. And the two formulations, the cost function over here and the loss function that we had earlier, are also going to be equivalent in this case. Some of the differences are that the scaling that we have that 1 over 2m scaling factor. It doesn't change the solution, just scales the loss value. And little notational issues here and there because of the matrix operations. Maybe we could like go into an example, but now let's just sort of delve into like the advantages of some of these. In general, you might think that the matrix formulation is preferred in more advanced settings because it's more compact, makes the derivations clearer. It's easier to implement computationally, and really it generalizes better depending on the kind of methods that you're using and the applications that you have. But both formulations solve exactly the same optimization problem, so they're going to be equivalent in that regard. But if you are working with this hypothesis function and you start to work with large data sets, it'll require some more efficient computation. So instead of writing the equations for individual data points, you might want to express everything in a vectorized form instead. So in this case, the hypothesis function becomes h theta x is equal to x times theta. And here the x is again a feature matrix of size m by n. M are the number of data points, n are the number of features, and theta is the parameter vector. It's of size n by 1 as well. The cost function then can be written in vectorized form, and it's much more compact, it's more computationally efficient, it's easy to implement using libraries like NumPy or PyTorch. And really, to handle large data sets efficiently, you really need to use the vectorized representation. All right. Let's see if we can get to some of the details of formulating this optimization problem now. So we know that the goal of linear regression is to minimize the difference between the predicted values and the actual values. And so this is achieved by minimizing some loss function that we saw, commonly the mean squared error, the MSE that we saw. And the linear regression model is typically just represented as y is equal to yx beta plus epsilon, where y is the vector of dependent variables, x is the design matrix of independent variables, and beta is the vector of model parameters, and epsilon is just the error term that we have. The MSE loss function is then defined as 1 over n yi minus y hat I squared, where yi is represents the actual values, and y hat I represents the predicted value, and n is just the number of data points. And again, minimizing the MSE will yield the optimal model parameters. Very nice. So, in linear regression, the cost function that we often talk about is that MSE, as we'd mentioned, and it helps us measure how far off our predictions are from the actual value that we might have. Quite simply, the MSE is going to be calculated using this formula that we have, of course. And our main goal here is to minimize the MSE, which will help us find the best fit line that we're looking for. So how do we go about doing that? Well, we use some kind of optimization techniques, like gradient descent, to minimize the MSE. It's this iterative approach, which we're going to see next, rather than that closed form solution that we saw earlier. This approach allows us to tweak the coefficients step by step, and gradually we minimize the cost function and boost our model's accuracy. How do we go about doing that? What exactly does this gradient descent stuff do? Well, gradient descent is one of the most important optimization algorithms that's used to train machine learning models. Most of machine learning is optimization or optimization adjacent, at least. You could definitely say that. It starts with some initial guess, in this case, for the model parameters, and then iteratively updates the parameters in the direction that reduces the loss function the fastest. The update rule is over here, and theta I are the parameters. Alpha is the learning rate, and the partial of j with respect to theta I is the partial derivative of the loss function. And this process continues. I don't know what happens to my cursor. This process is going to continue until the algorithm converges to a minimum or until some maximum number of iterations is reached. And we can formalize this idea as well. And let's see that here. There we go. So we can see that more clearly over here, where alpha is the learning rate, and the partial is the partial of the cost function with respect to the theta in this case, and the gradient of the cost function, which we see over here, tells us how to adjust theta to reduce the error. And you can see how the vectorized form of the gradient makes the computation efficient, especially for large data sets that you might typically face in machine learning nowadays, machine learning and data science, I should say, nowadays. This is, of course, different from the closed form solution that we saw. The closed form solution for linear regression allows us to directly compute the optimal model parameters without iterative methods like that. And that's possible because the loss function, the MSE, is convex and differentiable, right? So we're really mathematically aiming to minimize the MSE, which is calculated as this, and the yi are the observed values, and the y hat I equal xb are the predicted values based on that design matrix X and the parameter vector beta, and taking the derivative of MSE with respect to beta, setting it to 0, finding the minimum, and solving the beta yields that closed form solution that we saw earlier. So this direct non-iterative solution provides the optimal values of beta that minimize the MSE, which is kind of very lovely and unique to this linear regression. This closed form solution is like having the direct formula, while the gradient descent is like making educated guesses and improving them. By the way, I should make a point here. The assignment operator or definition operator, that symbol over there, means that something gets updated to or becomes equal to in this gradient descent formula that we have. It's not a mathematical equality. Most of you probably know that. In case you hadn't seen it, though, it's good to sort of clarify that. But it's an assignment operation showing how we update our guess, and the notations usually used commonly in algorithm descriptions and, of course, in computer science to distinguish assignment operations from equality. All right, the equality operator, I should say. Here we go. All right, let's look at a simple example in this case. So in this case, the closed form solution solves it in one step using matrix algebra, right? And the gradient descent in this case starts with a guess. Maybe m, I don't know there's my cursor. Maybe m equal to 0, b equal to 0, and oh my gosh, this cursor keeps disappearing. And it gradually keeps improving it using it should be an assignment operator. There it is. Oh Lord. There we go. Okay. I'm going to stop trying to use my cursor. It disappears on my side so I can't see where it's pointing. But both methods will eventually get to y equals 2x. But the gradient descent takes multiple steps to do so. So why should you use each method, or when should you use each method? For our simple examples, the closed form solution is clearly better, but for real world problems with millions of data points, gradient descent becomes necessary due to just computational limitations of matrix operations, right? The assignment in gradient descent is indicates that we're updating our guess each time, and it's showing how the value gets updated based on the current value as well. So I think, oh, you know what? One of the things I should point out over here, and it's kind of hard to read as well. This says may converge to local minimum, but global for linear regressions, convex cost function. Ooh, that totally got cut off. Apologize for that in the PDF, so hopefully it'll be better. But the statement may converge to local minimum for gradient descent is technically true in general, but for linear regression specifically, the cost function is convex, so there's only one minimum, the global minimum, right? Thus, for this specific case, where linear regression with MSE loss, both methods, both methods will find the same solution because the problem is convex. The cost function for linear regression is convex. There's a single global minimum. This is what guarantees that both the closed form and the gradient descent, with the proper learning rate, will find the same solution. And in general, it'll be good to sort of emphasize the importance of choosing an appropriate learning rate alpha. If alpha is too large, the gradient descent may overshoot the minimum or fail to converge. And if it's too small, convergence may be very slow. Also, the closed form solution can suffer from some numerical instability when x transpose x is ill-conditioned. That is, it's nearly singular. And in those cases, regularization techniques, like we'll see with ridge regression, adding a penalty term, lambda I, are used to stabilize the solution in that case. All right, I don't want to spend too much time on that. But the key metrics that we'll cover for evaluating these kinds of models and diagnosing our linear regression model are, of course, the MSE, the mean squared error, which you saw, but also R squared, which I guess we can see over here, and you've probably seen before, and the adjusted R square that we have as well, which is represented over here. The MSE quantifies the average squared difference between the actual and predicted values, and lower MSE indicates better model fit, but it's sensitive to outliers. R squared, in this case, represents the proportion of variance in the dependent variable that's explained by the model. It'll go from 0 to 1, as you probably know already, and the higher values indicate a better fit, but it increases with the addition of predictors, even if they aren't significant. So you'll want to sort of take care of that. And so that's why the adjusted R square penalizes the addition of predictors that are insignificant. And so it provides a more accurate assessment of the model fit, especially when you compare models with different numbers of predictors. And so when you're trying to choose a metric, the MSE is useful for direct comparison of prediction accuracy, but R square or adjusted R square are good measures of sort of overall model fit that you have. You can also use diagnostics like residual plots, and influence measures can also help assess both model assumptions and identify outliers or nonlinearity that may be present as well. All right. So, we're talking about this idea of diagnostics and validation, and I think the residual plots are going to be very important. QQ plots, you can use that for normality, the residual plots for heteroscedasticity, tough to pronounce. But evaluating the model really will help you understand how well it's performing. R squared is probably a very nice handy metric that'll tell you the variance in your dependent variable. Well, how much of that variance can be explained by the independent variables. And it's like a little scorecard that you'll use for your model. The adjusted R squared, as we mentioned, takes into account the number of predictors we have in our model, so it gives a clear picture, especially when we're dealing with multiple regression, as we'll see in a bit. Residual analysis can be done by looking at the residual plots, and you can evaluate how well the model fits the data and check to see if you're meeting the assumptions of regression. That might be a crucial step in ensuring that the model's reliable. But the payload of any regression analysis hinges on accurate model evaluation metrics. So, of course, it's important to really understand how to apply and use these metrics as you're doing it, but it's also important to understand the assumptions of linear regression as well. And so there's several important assumptions that it has, the primary one being linearity, that the relationship between the input features and the target variable, input feature and the target variable, well, we'll see in the case of multivariate regression as well, variables, target variables, is linear. If the true relationship is nonlinear, linear regression understandably won't perform so well. It also assumes that the observations are independent, that observations in the data are assumed to be independent of each other, and violations of that assumption, like autocorrelation, often seen in like time series data, can lead to biased estimates. So it's crucial that the observations are independent of one another and they don't influence each other if you're using linear regression. Then, of course, there's homoscedasticity, which is the constant variance of errors. And this just means that the residuals or errors that you have should have a constant variance, no matter what level of the independent variable you're looking at. The variance of errors should be constant across all levels of the input. And if the errors vary significantly, it can sort of distort the predictions that you have. And finally, normality. The residuals, or the errors, as we said, are presumed to be normally distributed. This is especially important for statistical inference when we're interpreting confidence intervals or p-values, and helps ensure our model's reliability as well. Some of these assumptions in real world data are often violated, though. So, part of your job as a machine learning or data science practitioner will be to detect and account for issues, especially like nonlinearity and homoscedasticity. That's going to be, I think, something that comes up practically a lot as well. All right, so what are some of the limitations of linear regression, other than the ones we saw when they violate the assumptions as well? Although it is simple and interpretable, right? That's the big benefit of it. It has several limitations. It has big sensitivity to outliers. The outliers can disproportionately affect the model because it minimizes that squared error. The linearity assumption, of course, it can't capture nonlinear relationships. Overfitting, if you have too many features, the model's going to overfit the training data. And the feature scaling, if the features aren't properly scaled, the gradient descent may converge very slowly. Okay, so also what we want to consider is that there isn't just one kind of linear regression, the simple linear regression, but there are different forms of linear regression, and they serve different various analytical needs. Simple linear regression, of course, offers a simplistic view, capturing relationships between one independent variable and one dependent variable, usually. Multiple linear regression, on the other hand, broadens its scope to several predictors, and it accommodates more intricate sort of data interactions as well. And then you can also have polynomial regression, which is an alternative for scenarios where they might be displaying some kind of non-linear relationships by also integrating polynomial terms. And this enhances the model's adaptability and its predictive capability. So, linear regression is, of course, the most basic form, and that's the one that's useful for straightforward relationships like predicting house prices based on square footage that we talked about earlier. The multiple linear regression, where you have these multiple independent variables, it can model more complex relationships like maybe predicting house prices based on size, location, and sort of the number of bedrooms. Boy, let me think about this polynomial regression a little bit. That's going to be used when the relationship between the variables is nonlinear. And you can include polynomial terms by including them. You can maybe better fit data that exhibits some sort of curvilinear patterns. Um, I'll have to think of something to relate it back to housing again as well. But let me come over here and let's look at the mathematical formulation of these different ones, right? We began with like that nice simple linear regression. That's the foundation of regression analysis. In that model, we have just one independent variable and one dependent variable. Hoping the mouse is pointing correctly when I go over there. And the equation y is equal to beta naught plus beta 1x plus epsilon represents that relationship. Beta naught is the y-intercept, beta 1 is the slope, and the matrix form is, as we saw, particularly useful for computational purposes. X in this case is n by 2 because of the intercept term. And this formulation allows us to use linear algebra for very nice, efficient computation of the coefficients. I think the housing price example is particularly intuitive here. So, you can keep that in mind, thinking about the house prices maybe based on the size of the house, the square footage of the house, or something along those lines. In multiple linear regression, of course, we extend our model to now include multiple predictors. This is much more realistic for real-world applications. Outcomes are rarely influenced by just one factor. And you notice how the matrix dimensions change in this case. Um, X now has P plus 1 columns where P is the number of predictors that we have. And the plus 1 has to account for the intercept term. And so the example in this case again is with the housing and in this case the housing example that we have, but now we can capture more complex real world scenarios, can consider multiple factors that can influence price. And similarly, if you wanted to do student performance, that'd be affected by various factors too. It's a perfect fit for multiple regression or multiple linear regression. Another variation that we should sort of consider is this multi-variate regression, which is one of the most complex forms of regression, where you simultaneously are predicting multiple dependent variables. from your same set of predictors that you have, the P predictors that we have. This allows you to capture relationships not just between predictors and outcomes, but also among the outcomes themselves as well. And the matrix form here becomes more complex. I think it got cut off a little bit with that background. I apologize for that. With Y now being a matrix rather than just a vector, as we saw previously. B in this case is also a, uh, a matrix, and it contains the coefficients for each predictor outcome pair that you have. And the example that you can see over here can show how multivariate regression can maybe handle complex scenarios where you need to predict multiple related outcomes. In the real estate example that we have over here, price, rent, and time on market are probably correlated in some way. So it makes this approach, sort of more relevant and appropriate. And it's particularly maybe illuminating um, because factors that affect price likely also affect rent and the time that it stays on market. Now, this is not the same as running separate regressions. I think that's an important delineation to make. And the error terms are also correlated across the equations. And you can test hypotheses about effects on multiple outcomes simultaneously with this. And the implementation requires some methods like maybe MANOVA or SIR. Maybe we'll see. I think I've got like the code for it. It got cut off, so I was considering maybe not putting it in there. Maybe in the PDF, I think it'll show off. It'll show up better. And in terms of the correlation between outcomes in multivariate regression, the error terms the epsilon across equations are often correlated. That's why you need multivariate methods like MANOVA or SIR. The MANOVA examples that we'll have, I think we're going to use stats models for that, which is also appropriate for hypothesis testing, which we're going to see in a lab as well, but not for directly estimating coefficients. For estimating coefficients, what you need is that seemingly unrelated regression, SIR. We'll see that as well. Or custom implementations might be more appropriate. But SIR is used to, for example, to account for correlated errors across equations. But these aren't just separate regressions. I think that's the important point. The multivariate regression is not the same as running separate regressions because of the shared predictors and the correlated errors that we have. All right. So we'll conclude this by focusing on this multiple linear regression as it's the most commonly used in practice. It's the most common form that you'll find of linear regression. It strikes a balance between simplicity and power, and it allows you to account for multiple predictors, but still maintains interpretability, which is huge, especially as we look at more of these opaque box algorithmic approaches, especially with deep learning, etc. as well. The formula might, for those that are coming to it for the first time, look a little bit intimidating, but each component has a clear interpretation. Beta naught is the baseline. Each beta I represents the effect of the corresponding predictor xi, and the epsilon captures what the model couldn't explain. And I think that should be relatively clear over there, and especially that has such a wide applicability in terms of applications. And so, although more complex models do exist, the multiple linear regression often just provides the best balance between both model complexity and practical utility. But some of the key points that I do want to highlight over here, by the way, the formula shows us that even though you have multiple predictors, you're still working with a single equation because you have a single outcome. That's different from that multivariate regression where you had a system of equations. But the key points are that the multiple in this case refers to the predictors, not the outcomes in multiple linear regression. And multivariate regression was to the outcomes as well. Each beta over here in multiple linear regression, each beta coefficient has a practical interpretation of some sort, and the applications span many fields, like from economics to healthcare to you name it, it's over there. Oh, and the error term, of course, captures all the unmeasured factors. But some common pitfalls that you might still stumble across are things like multicollinearity between predictors, overfitting with just having too many predictors, and you might have to, sort of really focus on feature selection as well. So these different use cases and the different kinds of regressions can get a little confusing. Hopefully, a table like this will help you find the differences, some at least summarize the differences between things like simple linear regression, multiple linear regression, the number of independent dependent variables, and the multivariate linear regression approach as well. All right, so the final thing that I want to sort of touch upon over here is that you can have the matrix formulation for all those three kinds of linear regressions that we saw, and you see it's this nice compact formulation that we end up with. And the implementations in code are similarly um, very simple. They're very quick and easy to do. And I think this one, the linear regression, I think is in there pretty well. The others I think got cut off, and I apologize for that a bit. The main difference here is in the number of outputs, the y variables that you have. In multiple regression is just a special case of multivariate regression with like q equal to 1. You can think of it that way. And multivariate regression also allows for correlation between outcomes. But that, as you saw, that matrix notation just makes things so much easier. And so here's that final implementation of both multivariate regression. Oh my gosh, yeah, this got cut off. I'll have to find a different approach to putting it in there. So this should show down here. I think here's the MANOVA approach, and that got cut off, and I'll add that in. But that's from stats models that it comes in, and you just basically give it a MANOVA dot from formula, and then you do the model fit. And then we have the seemingly unrelated regression SIR as well, which you can utilize. I'll have to fix that in the in the uh, in the PDF that we have. But one of the last couple of things that I want to touch upon is this idea of overfitting and underfitting. These are two critical challenges in machine learning. We've sort of touched upon a little bit about the bias variance trade-off, but overfitting happens when the model memorizes the training data, including the noise, instead of generalizing. And you can think of underfitting as occurring when the model's just too simple to capture the underlying patterns in the data. And so to address these two issues, we can use things like cross-validation, pruning, regularization, and feature selection to sort of balance between the model complexity and the performance. And achieving the right balance between model complexity and generalizability is essential in regression methodologies. Overfitting leads to models that perform really well on training data sets, but falter significantly in real-world scenarios with unseen data. On the other hand, underfitting gives you these oversimplified models that just fail to capture essential patterns. And so by understanding the dynamics behind these phenomena, such as maybe their causes and their effects, we can implement strategies like that cross-validation, feature selection, regularization that can help protect against that, and hopefully give us models that generalize well from the data. Overfitting and underfitting are specifically manifest in regression models. Overfitting is with too many parameters or high degree polynomials, and underfitting with overly simplistic models that you might have. And so that leads us to the idea of also trying to understand model complexity. It isn't just about the number of parameters, but it's about how flexible the model is in fitting patterns in the data as well. But the number of parameters is usually a good proxy for that complexity, and that's why it's sort of there as as the main issue that we have. So here's a simple example with temperature prediction that might help in this case. The temperature example basically shows how different levels of complexity affect model performance. If you had a constant or a linear model and it's going to be too simple to capture seasonal variations, but a very high degree polynomial might perfectly fit the training data, but it won't generalize. You have to sort of find the right balance. And the just right model balances this idea of complexity with generalization. In this case, it has just enough parameters to capture the important patterns like the seasonality and trend, but not so many that it also, captures the noise in the data as well. And so, and if it doesn't do that, then it'll generalize well to new data. So how do you go about choosing the model complexity that you might have? I guess I should add in model complexity over there then rather than how to choose complexity. But the key to choosing model complexity is to balance the model's ability to fit patterns in the training data with the ability to generalize to new data. That's the one thing you want to keep in mind in regards to that. So you can have some signs of you're underfitting in this case or signs that you're overfitting, but really you want to sort of find the balance as much as you can, and look to do that. This cross validation and learning curves I think are probably the most essential approaches. But something else that you can do is use regularization to improve model performance and also prevent overfitting. There are several kinds of regularization that are used widely. Lasso regression uses that L1 regularization to shrink the less important feature coefficients to zero, basically performing feature selection. Ridge regression uses L2 regularization, and so it penalizes large coefficients to help reduce the overfitting. ElasticNet ElasticNet combines both L1 and L2 penalties, and it offers this flexibility for datasets with correlated features. The techniques are widely used in machine learning, and they help sort of ensure that your models are more robust and more interpretable as well. They're a very powerful suite of methods um, that are employed to enhance linear regression models, especially in regards to this idea of overfitting. And I think these are the ones that you'll want to sort of keep an eye out for. And the strategic application of these techniques will definitely improve the predictive accuracy that you might have, but also at the same time clarify the model structure. Now, in terms of implementation, there are a few libraries that are widely used. We're going to be delving into all of these. This is what we're going to be doing in all the labs that we have. This is the thing that will occupy us for most of our time. NumPy and Pandas are used for data manipulation and matrix computations. Scikit-learn offers these tools for building and evaluating regression models. And a typical workflow will involve importing the data, fitting a model, and visualizing results, right? And so visualization tools like Matplotlib, Seaborn, etc., will help interpret the model's performance by plotting the regression lines and the residuals. And implementing linear regression in Python is really streamlined by using libraries like NumPy for these numerical operations. Pandas, of course, also is essential for data manipulation, and scikit-learn has so many great sort of robust machine learning models. We're going to be really looking into that in a lot of detail. So through some of these practical code examples that we'll see, we'll illustrate how to load data, build, and then train a linear regression model, but also still efficiently extract outputs from there. We'll also employ these visualization techniques to help us to graphically represent the regression outputs. Also help reinforce our understanding of the model's effectiveness and its predictive capabilities. I think this will help build a solid foundation in the coding practices, and that's going to be essential for any sort of aspiring machine learning practitioner or data scientist, I'd say. All right, I know I've gone on for a lot longer than I'd promised you I would, and I apologize for that. Here's a little summary, and there's some additional discussion questions I was gonna delve into, but for now, let me just end the video where we are. Give you a little bit of references as well. I hope you hung in there for it. It wasn't too bad. Great job hanging in there, and we'll see you around. All right, bye bye.